Hi everyone, today we're doing notes for 3.2, which is on measures of variation. The range is the difference between the largest and smallest values of a data distribution. Here's our first practice. A large bakery regularly orders cartons of Maine blueberries. The average weight of the cartons is supposed to be 22 ounces. Random samples of cartons from 2 suppliers were weighed. A says, compute the range of carton weights from each supplier. So from supplier 1, we can see that the largest value is 27. The smallest is 17. So if I subtract that, we have a range of 10. From supplier 2, the largest is 27, and the smallest is 17 again. So we have a range of 10. B says, compute the mean weight of cartons from each supplier. So supplier 1, let's add these up, 17, 22, 22, 22, and 27. Divide by 5. That gives us a mean of 22. For supplier 2, we have 17, 19, 20, 27, 27. Divided by 5. And again, we have a mean of 22. So C says, look at the 2 samples again. These samples have the same range and mean. How do they differ? The bakery uses 1 carton of blueberries in each blueberry muffin recipe. It is important that the cartons be of consistent weight so that the muffins turn out right. So if we look at these and we try to compare them, from supplier 1, these are more consistent. We have 3 cartons that have the exact weight. Supplier 2, this varies more. There's 0 cartons that have the exact weight. So looking at this, we would probably want to choose supplier 1 so that way that those muffins turn out right. Okay, sample standard deviation. Here's our formula. S is equal to, we see this symbol is a sigma that stands for the summation. So we're going to be adding together each x minus x bar, which if you recall is the sample mean squared, divided by n minus 1. So we're going to do a guided example to find the sample standard deviation of the ages of my kids in months. And this is when I wrote this. They're a little older now, but that's okay. We have 48, 74, and 91. First, find the mean, x bar, sigma x divided by n. So we're going to find the sum of all the data and divide by the sample size n. So 48 plus 74 plus 91 divided by 3 is 71. To do the sample standard deviation, we're going to find the sum of squares by finding the difference between each value and the mean. Then we square the difference, and then we find the sum of these. So this is all written out in the table. We're going to divide by 1 less than the sample size. So in this case, our sample size was 3, so I'm going to divide by 2. And then take the square root to find the sample standard deviation. In this case, the sample standard deviation of the ages of my kids in months is 21.656 months, or just under 2 years. All right. Big Blossom Greenhouse gathered a random sample of mature peak blooms from hybrid B. The 6 blossoms had the following widths in inches: 5, 5, 5, 6, 7, and 8. Okay, so we need to find the value of n and the mean x bar. Please do this. If you recall, n is the sample size. So our n is 6. X bar, remember, is our sample mean. So to find that, we're going to do 5 plus 5 plus 5 plus 6 plus 7 plus 8. Divide that by 6, and our sample mean is 6. Okay, so I'm going to fill this x bar in our table right here. X sub I means each of the individual values. So we have 5, 5, 5, 6, 7, and 8. Then we're going to do each value minus the mean. So 5 minus 6, which is -1. Then we have 6 minus 6, which is 0. 7 minus 6, which is 1. And 8 minus 6, which is 2. Then we have to square each of these values. So I have -1 squared is 1. I have 0 squared is 0. 1 squared is 1. And 2 squared is 4. Then I take the sum of each of these. So 1 plus 1 plus 1 plus 1 plus 4 gives us 8. Now to find the sample standard deviation, we're going to take the sum of each x minus x bar squared, so that's our numerator, so my 8 goes here, divided by n minus 1, so that's 6 minus 1, and then we're going to take the square root of this. So that's the square root of 8 over 5, which gives us 1.26. And our units here are inches. So that is our standard deviation. Measures of variation give information about the spread of data. The range tells us the difference between the highest data value and the lowest. It tells us about the spread of data, but does not tell us if most of the data is or is not closer to the mean. The sample standard deviation is based on the difference between each data value and the mean of the data set. The standard deviation gives an average of data spread around the mean. The larger the standard deviation, the more spread out the data are around the mean. A smaller standard deviation indicates that the data tend to be closer to the mean. The variance tells us the square of the standard deviation. As such, it is also a measure of data spread around the mean. All right, so population parameters, where n is the number of data values in the population and x represents the individual data values of the population. Our population mean is mu is equal to sigma x divided by our capital N. Population variance, sigma squared, is our sum of x minus mu squared divided by capital N. And the population standard deviation is sigma, and this is the square root of the variance. So we have square root of the sum of x minus mu squared divided by capital M. So a couple of reminders. Mu is the population mean. X bar is the sample mean. Mu is equal to x bar. Sigma is the population standard deviation. Capital N is the population size. S is equal to the sample standard deviation, and lowercase n is the sample size. Okay, practice 3. Here's our data set 1, 2, 3, 4, 5. Compute the sample standard deviation S and the population standard deviation. Sorry, there we go. And the population standard deviation sigma. Please take a minute and do so. Okay, so mu is our x bar, so we have to do 1 plus 2 plus 3 plus 4 plus 5 divided by 5, which is 3. So I'm going to fill that in our table. And remember, our capital N is the same as our lowercase n, which is 5 for this case, because this is our population that we're working with. All right, so our values are 1, 2, 3, 4, and 5. X minus x bar, so I have 1 minus 3 is -2. 2 minus 3 is -1. 3 minus 3 is 0. 4 minus 3 is 1. 5 minus 3 is 2. Then we square each of these. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. Find the sum. 4 plus 1 plus 0 plus 1 plus 4 is 10. So now, to find the sample standard deviation and the population standard deviation, it's very similar, but notice the difference is in the denominator. For sample standard deviation, we're doing our n minus 1. For population standard deviation, we leave it as our capital N. Okay, so for the sample, S is equal to square root of 10 divided by 5 minus 1, which is square root of 10 over 4, which is 1.58. Population standard deviation, sigma, is square root of 10 minus 5, which is 1.41. So we have our sample standard deviation is 1.58, and our population standard deviation is 1.41. Again, you can do this in the calculator if you do stat calc one variable statistics, as we had described before. Just make sure you put your data into the list before you go to calculate that. Okay, just to make sure we know what all of these on this screen mean. This X bar, this is your sample mean. Sigma X is the sum of the data values. S sub X is the sample standard deviation. And then sigma X is the population standard deviation. Here we see N, if you recall, is the sample size. And again, I'll highlight, once you have your data in a list, then you can hit stat calc, one variable statistics. You also might see a printout from Minitab, which is a computer program. We're not going to use the program, but you need to understand the printout. There are some problems involving this in the textbook. So here, N, this represents the sample size. Mean here, this is your X bar, which is your sample mean. You can see there's median on here. And here, STDEV, this is our S, or our standard deviation. Later on in the semester, we'll go over what some of the other things mean, but for right now, we just need these. Next, we have Chebyshev's theorem, and this says, for sample data with a mean X bar and standard deviation S, at least 1 minus 1 over K squared, fractional part of the data, must fall between X bar minus K times S and X bar plus K times S. So the results of Chebyshev's theorem say that for any set of data, at least 75% of the data fall in the interval from mu minus 2 times the standard deviation to mu plus 2 times the standard deviation. At least 88.9% of the data fall in the interval from the mean plus or minus 3 times the standard deviation. And at least 93.8% of the data fall in the interval from the mean plus or minus 4 standard deviations. Chebyshev's theorem applies to any distribution, and it tells us the minimum percentage of data that fall between the mean and any specified number of standard deviations on either side of the mean. A minimum of 88.9% of the data fall between the values 3 standard deviations below the mean and 3 standard deviations above the mean. This implies that a maximum of 11.1% of data fall beyond 3 standard deviations of the mean. Such values might be suspect outliers, particularly for a mound-shaped symmetric distribution. So here's our last practice. The East Coast Independent News periodically runs ads in its classified section, offering a month's free subscription to those who respond. In this way, management can get a sense about the number of subscribers who read the classified section each day. Over a period of 2 years, careful records have been kept. The mean number of responses per ad is X bar equals 525 with a standard deviation S equals 30. So I'm going to underline these important facts that we have here. And it says determine a Chebyshev interval about the mean in which at least 88.9% of the data fall. So we can see up here, here's our 88.9% of the data. It's going to fall between our mean plus or minus 3 standard deviations. I'm writing this in the notation for a sample. I would like you to find this interval now, please. Okay, for the lower bound, we're going to subtract. So we have 525 minus 3 times 30. That's going to give us 435. For the upper bound, we add 525 plus 3 times 30, and that gives us 615. So our interval is going to be 435 to 615. You always write it as lower bound, comma, upper bound. And so we can say at least 88.9% of the data is between 435 and 615 responses. And that's the end for today.